diagonal, make it the radius of a circle that you sweep down until it makes a straight line, and you get 1/2 plus root 5 over 2 to 1. That divided by that gives me the golden ratio. Okay? So it does provide a geometric relationship that we can see in shapes. I'm not going to cover a lot of the real-world examples of where it's in the Apple logo, or Nike uses it, or we put it in the it's in the Parthenon and all those things. Again, sometimes that depends on where you measure from. And so if I want to say, well, this is a golden rectangle right here, as long as I measure from the door jambs out, or if that doesn't work, maybe I'll measure from the inside of the door jambs. Or I can just, I can make the rules whatever I want. We got to be careful not to force things to fit where we want them to. But if it's there, let's identify it. Let's recognize it. So this creates the golden spiral. Again, we've got a 1 by 1. Next Fibonacci number is 2, 1 by 2. Now a 2 by 3. Now a 3 by 5. Now a 5 by 8. Now an 8 by 13, and so on and so forth. And if you add these, they make squares. Notice the area of these squares. It's a 1 by 1, a 2 by 2, a 3 by 3, a 5 by 5, an 8 by 8. These are Fibonacci numbers. And when you trace an arc out to make these pretty curves from corner to corner, they make what's called the golden spiral. Now, before I go any further, does this shape look familiar to any of you? Where have you seen this? You're gonna talk about some of my slides, but let's have it. Where have you seen it? Where? In Moana, yes. I know what you're talking about. The necklace she wears? Yep. Okay. Anybody else recognize this shape anywhere in nature?
Shells.
Yeah. Any particular shells you've seen? Nautilus. Okay. We are going to talk about nautilus. In the back. Did she have one? Was that hers? I'm sorry. All right. Well, just to kind of weird you guys out a little bit, this is a recursive spiral. It spirals it on top of itself. So I can play this forwards and backwards. Going forwards or backwards. The spiral's increasing as you go out, or maybe as you're going in. That'll trip you out. Here we are. We finally made it. What does the Fibonacci series have to do with nature? Well, we've seen the numbers. What about this ratio? Sunflower seeds, pineapples, pinecones, seashells, hurricanes, galaxies, sunflower seed. Do you see a spiral here? Hopefully you do. And if not, maybe this will help. There it is. Pick any point from the middle, sweep your way out. 21 seeds in that spiral. We'll start here and we'll take a short path. 55. Wait, how's that 55? I think those numbers are wrong. 21, 34, 55. Yeah. This isn't my picture. I'll blame Golden Spirals, whatever, that website there. But the pattern is legitimate, that any place you count out, it's going to be a Fibonacci number, and it's going to follow a Fibonacci spiral. Why is that? Well, the reason that scientists have assumed, they've deduced, they've tried to theorize, is that it makes it very efficient in terms of packing seeds into the sunflower portion. We see this in pine cones. Whether you count clockwise or counterclockwise, which spirals do you want to look at? Well, I see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Each one of those bends, if you count each one of these spirals, one of those numbers is going to be a Fibonacci spiral, or Fibonacci number. And if you trace out these spirals, well, this has 13 spirals this way. It has 8 spirals the other way. Oh yeah, those are Fibonacci numbers. 13 divided by 8 is not the golden ratio, though. Remember, the golden ratio is that it gets closer and closer to this. We do have to be careful with saying, well, that's definitely a Fibonacci series. It has 2 numbers in a Fibonacci series, and it leads to a Fibonacci spiral if this thing was, as big as a football stadium, and you could keep counting. Then you could count those ratios. I bring up honeycomb. There's no Fibonacci sequence here, but as I mentioned with the sunflowers, packing the seeds in the smallest amount of area as possible, that is what a sunflower does. And so if we took a honeycomb and wrapped it around a fruit, you would get pineapple. There it is.
Yeah.
Okay? It's got this shape right here, wrapped around a pineapple. And let's see, if you want to count them this way, 8 rows this way. Or if you want to do it taller, medium slope, 13. Anybody want to guess the next number?
21.
Hey, it's 21. There you go. We're going to do them tall ways, okay? They're all like that. They're all like that. Big or small, their size is the size of each portion here is related to the size of the pineapple. So we started late, and my timer is based on. Okay. I only have 200 slides left, so. Okay. Guys, this was really hard for me because when Ashley asked me to do the Fibonacci series, I had heard and seen and even spoken about what most of you probably walked in assuming, that Fibonacci is all over the place and it answers all these questions about the math and nature, and some of that has been falsified or blown up to an extreme, or just, people just are repeating things that they've heard. So, I put a lot of links on here. I have 4 at the end that if you really want to know more about these are the links I'm going to ask you to turn to, because you really get both sides of, well, I see Fibonacci in everything, and another person says, no, it's the big lie. It's the Fibonacci. This one here, that's pretty common right there, the beauty of the human face. And I can draw those swirls all day long on anything I want. I don't really see how this fits. I don't know, maybe that's just me. Her head has a nice curve here, but I know a lot of people whose heads aren't shaped like that. So is this the image of beauty? Well, that's in the eye of the beholder. This one here, that's a fun one. That one does follow Fibonacci series. So sometimes it's there, sometimes it's not. These Fibonacci spirals on Romanesco broccoli. I have seen that. I've not eaten it, but they sell it at a farmer's market around the corner from my house. It's awesome to look at. So if somebody tells you that it's everywhere, you need to question that. That's what science is, right? We question things. We want to know what's true and what's not, whether we hear it in the news, whether we read it in a science textbook, whether it's something our parents told us. Good scientists, they ask questions, and they want to know for themselves what's true and what's not. So here's my disclaimer again. This is not going to fit all shells, storms, and galaxies, or other shapes that we've looked at. It's not always a Fibonacci series, okay? There are other series, and that's why I do want to talk about a couple other mathematical relationships that show up in nature, but not just always Fibonacci. There are other spirals that exist. For the nautilus, which somebody mentioned, its growth rate actually follows a spiral of about 1.587, not the 1.618, blah, 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 blah. Let's just round it to 1.6. 1.6 is not the geometric mean. It's not the golden ratio, because it has to get closer and closer to that. So if you just say 1.6, I can find that anywhere. I could say, well, the ratio of people with jackets on to people without, golden ratio. Or maybe the people who are wearing glasses tonight versus the ones who aren't, golden ratio. I can find those numbers wherever I want to. And we don't want to do that. We just want to see it where it actually is. So unfortunately, seashells, hurricanes, galaxies, not Fibonacci, but they do follow another spiral. That's called the logarithmic spiral, of which the Fibonacci spiral is a special case. René Descartes, this is the one who said, I think, therefore I am. Yep. And then he went into a bar one time and he got some drinks, and the bartender thought he was done. He said, are you finished? And he said, I think not. And then he disappeared. You'll have to think about that. This is also the guy, we had the Cartesian coordinate system, X and Y plane. Same guy. He was a philosopher, he was a mathematician, he was a theologian. The guy was what they call a polymath. This was discovered by him in 1638. So you're talking 500 years, 500 or 600 years, 400 or 500 years after Fibonacci came up with his special case of a logarithmic spiral. This is in polar notation, guys. Don't worry too much about what this is, but E is a very common number that we use in mathematics. It's like pi. It's like phi. These are irrational numbers. They go on forever and ever without repeating. If you have E raised to a trig function, you multiply it by an angle and you get R. What it tells you is that the the size of the spiral grows. Not that it's consistent like your cinnamon roll. No Fibonacci series there, no logarithmic series there. It's always the same width all the way around. But if we look at one of these, then the distance between the successive terms will follow a new pattern. What's the rule here? This is an easy one. Doubles, okay? And that's called a geometric series. So it's not a Fibonacci series, but it's a mathematical series that shows up much more commonly in nature, including some of those that I've already mixed with geometric, or with Fibonacci series. So you can see that it's getting larger. The angle here stays the same even as the pie slices get bigger. So here they are in shells, whether you're talking about the nautilus. Because it's in blue, it's going to be hard to tell, but right up here, the Fibonacci spiral, the golden spiral, comes way up to here, but you see your nautilus shell only comes to here. It does follow a Fibonacci sequence in terms of the number of chambers. It does follow, if you take any two portions of that, it is approaching the golden ratio, but it doesn't fit the golden spiral. So does that mean that it's just a happy coincidence? Or does that mean that it works for some things and we have to find some other mathematical relationship? Remember I told you mathematics is a language? It's a language for science. It tells us how the world around us works. It tells us how we understand and how we can quantify and relay that information to other things in the natural world. Storms and galaxies, I'm pretty sure this is Hurricane Irma. Florida's under there somewhere. And spiral galaxies, they follow. I mean, where do you measure from to try and even fit this into a mathematical pattern? Do I want to measure from here? Do I want to measure from here? This cloud, this cloud. Where's the center of this thing? This is, especially for something like meteorology or astronomy, it's an inexact science where we can make predictions and we find models. And those models help us to make predictions that then we find evidence that confirms that theory, confirms that model, and then we refine that. And that is what science does. It just takes what we know, we try to find. We don't force it to fit a formula. We don't allow science to be forced into our preconceived notions. Whether that's a mathematical formula, whether that's what we were taught in grade school, whether that's what we hear on the TV, science should be something that we are making our own discoveries or confirming. You might not have time to go get a PhD in astrophysics, but there's plenty of information and cross-references, and that's what I had to do. I had some bubbles get burst. Fibonacci series doesn't fit everywhere. Too bad. Because I remember being taught and teaching Fibonacci, it's everywhere. It's not. It's not. And I'd be doing you a disservice if I said that. But these do follow loose patterns, and some of them, even the snail shells here, this is a logarithmic spiral. We can't follow that. But again, just like fingerprints, snowflakes, no two are alike. You can't just say every snail I ever investigate is going to have this perfect mathematical relationship because of variety in nature. That's what makes nature beautiful, isn't it? All right, last thing here with fractals. I'm closing in here. This is another mathematical pattern discovered by Benoit Mandelbrot. This is a Polish-born French-American mathematician in 1975. Okay, some of you are older than this understanding of mathematics, which is kind of cool. We're still learning things. I'm not much younger than this idea. It's a rough or fragmented geometric shape that you can split into parts. And all of those small parts look roughly like a reduced size of the original. Remember our honeybee family tree? That's a fractal. And no matter which way you draw that, it's going to follow Fibonacci numbers, and it is a fractal. But here's some in nature. The river delta. You've got large entry of water, and then each one of these little side streams are going to resemble, to some extent, I'm not going to be able to clone it and map it right on top, but it does resemble the original shape. Or maybe trees in the forest, tall trunk. Each branch has smaller branches, which have smaller branches, which have twigs, which have the veins in the leaves. They're all going to follow that pattern. These flowers, lots of flowers are going to exhibit fractal properties. And then the last one here, this fancy succulent. I don't remember the name of this one.
Aloe?
I don't think it's aloe, but it's one of the succulents. Okay. So how do we wrap all this up, and what do we take from this? Because there's some pretty cool things you learned, I hope, tonight, but maybe some things that you were disappointed. maybe some ideas that I ruined your understanding of what math looks like when we come to science. We don't approach science with preconceived notions that we're not willing to wiggle a little when the evidence shows us differently. Okay? So first thing we learn is that nature uses math. You can't argue with that. Whether the math drives the biology, or the biology follows the math, or leads the math, there's a connection for sure. And that's how we can understand nature. I've said this many times already, but if we did not have mathematics to understand the world around us, we wouldn't know anything. We wouldn't know anything. It follows predictable, repeatable patterns. This is how we know the world around us. One thing that you've heard maybe from another science teacher is that correlation does not equal causation. So if there is a relationship, we have to dig deep and find out, is there a pattern? And maybe it is for the honeycomb and for the pineapple and for the sunflower seeds, but they're trying to pack in the most amount of seeds in the least amount of space because that amplifies the opportunity for that organism to survive and reproduce. But is it caused because of that? That's a question that we have not answered. Don't force the formula. I think we've addressed that. I do want you to remember the next time it rolls around to celebrate Fibonacci Day. Would you like to guess what day that is? Think hard. Do you know what it is?
February.
Not in February. Not in January.
December.
We give
No.
up.
Use as many Fibonacci numbers in
November 23rd.
That's it. That's it. 1, 1, 2, 3. Very good. You win a sticker. Make sure you get it on the way out. All right. The last thing I'll say, guys, about this, and then I'll give you some links, and then I'll take questions if we have time. Do your own research. I learned more in the time that I spent for this than any of the seminars I sat under or the books that I read about Fibonacci. Because